Yeah, fix that. Yeah. So, that is yours.
Yeah, now I think how to do that.
Okay.
Okay, so this is going to be a slight change of topic. I know it's late, everyone's probably drunk, including me. So, anyway, it's time for some theoretical physics. I'm going to be talking about why understanding black holes is going to save physics. So the first thing we have to look at is why physics is in trouble anyways. And so the ultimate goal of theoretical physics is to find a theory that describes absolutely everything. That's what physicists are after for centuries. And what we were able to come up with are two theories that describe almost everything. And these two theories are a theory for gravity, it's called general relativity, it's kind of by Einstein, it describes the behavior of big things like planets and stars. And then on the other hand, there's this other theory called quantum mechanics that describes the behavior of small things like particles and atoms and so on. And for some time, these two theories sort of lived happily alongside each other, each of them describing sort of their own part of the world, except for one kind of object. And this object is a black hole. So the theory of big things sort of says black holes exist, they're objects, they're part of my theory. But the theory of quantum mechanics also has to say something about them. It doesn't like them. And well, I'm going to explain why it doesn't like them. There are very good reasons, and it turns out that the two theories disagree on a very fundamental level. And fundamental disagreements in physics, they have a special name, they're called paradoxes. In this case, it's the black hole information paradox, and so to understand what's wrong with physics, I'm going to explain to you what the black hole information paradox is. And to understand the black hole information paradox, you need to know what a black hole is, you need to know what information is, and you need to know what the paradox is. It's very straightforward. Okay, so let's start with black holes. You've probably all learned in kindergarten that masses attract each other, and this force between them is called gravity. That's wrong, forget about it. It's wrong. It's outdated. That's 500 years ago. What really happens is this. You have to take a massive object, I just say you take a mass, you put it in some space, and these are like your space coordinates. And now what's going to happen is the mass is going to suck up the space around it, kind of like this. So it's very much like a water drain where you have like a sink, and in the middle there's this drain, and so the drain sucks up the water around it. And then if you put two masses next to each other, they're going to suck up the space around them, and in particular they're going to suck up the space in between them, so it's going to look like they're moving towards each other, but really what happens is the space between them disappears because they're sucking it up. Right? So attraction is really just sucking up space. And that's what people call gravity. That's what theoretical physics call. Yeah, it's ridiculous. Don't take any of this seriously. Okay, so there are two more things you have to know about. Add this to my 10 minutes. Okay, so there are two more things you have to know about gravity. Sorry. Bigger masses, they suck in space more than smaller masses. Straightforward. And then another thing is, the further you away from the mass, the smaller the suction is going to be. Which is again very similar to this drain picture, where the further away you are from the drain of a water sink, the less you're going to feel sort of the pull towards the drain, right? So let's look at this drain thing kind of from above. So that's the drain in the middle, and the analogy is going to be the mass, and that's the amount of sucking. Okay, so now if you put a fish in the drain like this, if this fish doesn't want to be sucked in, what it has to do, it has to swim in the opposite direction, right, like this. And if you put the fish closer to the mass in the middle, it's going to have to swim faster to escape if it doesn't want to get sucked in. But now what happens if I make this mass in the middle very, very large, so the fish is going to have to swim even faster and faster and faster? Then Einstein comes and says, the fastest anyone can travel in this universe is the speed of light. That's like the ultimate speed limit of our universe. At least we don't have a counter experiment that says otherwise. So if this mass is so heavy that this fish would have to travel faster than the speed of light to escape from some distance around the thing, Einstein says, this is impossible, this area is kind of a point of no return. Fish has to travel faster than the speed of light. It can't travel faster than the speed of light. Not even light can travel faster than the speed of light. So this is the point of no return. We call this the horizon. And because not even light can escape from the region behind this horizon, to an outside observer, it's going to look dark. It's going to look black because no light comes from it. And that's what this is called a black hole. It's a region of space from which nothing, not even light, can escape. No light, no fishes, nothing. That's what a black hole is. And there are two more things you have to know about black holes. Black holes are very simple objects. So because no information comes from the black hole, the only thing you can say about them is kind of how big they are, or which is equivalent how massive they are. So a very simple object, only size matters. And there are too many analogies. The second thing is black holes can grow. So if you throw something inside, the black hole is going to grow. Its mass is going to grow by the amount of stuff you throw in. That's what you have to know. Okay. Now let's talk about information. That's the second part of the black hole information paradox. So information, you probably all know from your video cameras, if you take a picture of some object, this picture is going to be stored in a digital memory, and in the end it will have a form of a sequence of zeros and ones, just bits, right? And of course, cameras, they don't see everything. They don't like see through the fish. They don't see all the organs. They have a finite resolution, right? 10 megapixels or 20 megapixels. Good cameras even more, but they have a finite resolution, so they don't see anything. They can't resolve all the atoms and everything. But in principle, you could imagine that a camera, you could imagine a camera that can resolve actually everything. In principle, at least. So, in principle, the entire information content of an object can be stored in a sequence of 0 and 1s. Your information content, the fish's information, everything's information content can be written as a sequence of 0s and 1s. This is, I think, controversial. I don't think everyone believes in this, but I do. Okay, so let's say we have a perfect camera and this is the information content of a fish. Now we take a different object, let's say a banana, and it's going to have a different information content. Okay, now the next thing is we know that things change with time. So we have this fish, which is different from a banana, and both of them change in time. They age, they change their... The fish is going to get all the bananas. But the very important point is that they stay different. They stay different all the time and forever. And this is actually very essential and very fundamental principle of this theory of small things, of quantum mechanics, that things that are different stay different forever. Differences are conserved. And so another way of saying this is that histories of things are unique. So one thing that cannot happen according to quantum mechanics is that the fish and the banana independently evolve into the same object, like this. Because now if you see this object, you can't trace back his history unambiguously. You don't know whether it originated from a fish or from a banana. And this, according to quantum mechanics, cannot be the case. Histories are always unique. Different things stay different. And another way of saying this is that information about the history of things is always conserved. Information is conserved. That's what quantum mechanics says. So this can never happen, according to this theory of small things. Okay, and now we actually know everything we need to know to understand the black hole information paradox. So here's the paradox. We take a fish, we throw it into a black hole. The black hole is going to grow, and it's going to have the size or the mass of the first black hole plus the mass of the fish. Right? Because the black hole only cares about fish, it doesn't care about anything else because it can't emit any info. It doesn't, from the outside you don't see any information of the things that you throw in. And now you take a different object, you take a banana, you throw it into an identical black hole. Let's say the fish and the banana have the same mass, so they have very different information content, but they have the same mass. You throw them into a black hole, and what you're going to get is a black hole that's indistinguishable from this black hole. So here we have the situation where we start off. So on this, well, let's take this one. We start off with two systems that are different. Although the black holes are the same, the things we throw into the black holes are not the same. But we end up with the same object. And this is the same as we had before, where the fish and the banana evolved into the same object. You can't trace back the history. This is forbidden according to quantum mechanics, because quantum mechanics says information is conserved. But this theory of things, the theory of black holes, says this is perfectly okay and the information can get destroyed. And this is really the core of the black hole information paradox. One theory says black holes destroy information, and the other theory says, I don't like black holes because, according to me, information has to be conserved. And so this forces us to ask, so the reason why this is troubling is because these two theories, quantum mechanics and general relativity, the theory of gravity, is really all we have. We have some other candidates like string theory and stuff like that, but nobody knows if they're actually the theory of everything. These two theories are really all we have, and they contradict each other on a very, very, very fundamental level when it comes to the conservation of information. And so this forces physicists to ask some very uncomfortable questions, like, is one of them wrong? Or maybe both of them wrong. So I don't know, I don't think anyone knows, but one thing is clear, that we need to understand black holes better in order to answer these kinds of questions and hopefully one day save physics. That's all I have to say.